and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1730, shortest path to get food. Before we read the question prompt, just want to ask you to subscribe. You guys know the drill. You are starving and you want to eat food as quickly as possible. You want to find the shortest path to arrive at any food cell. You are given an m by n character matrix grid of containing the different types of cells. Star is your location, and there's exactly one star cell. Hash is a food cell, and there may be multiple food cells. O is a free space, and you can travel through these cells. X is an obstacle, and you cannot travel through these cells. You can travel to any adjacent north, east, south, or west tile from your current location if there is no obstacle. And we want to return the length of the shortest path for you to reach any food cell. If there's no path for you to reach, then return -1. Okay, that's the question prompt. Let's look at a few examples. So we looked at the question prompt. Now let's see an example. So in this first example, this is our current position, and this is a piece of food. What is the shortest path to reach it? Well, we could go down, right, right to reach it, or we could go right, right, down. Either way, it's going to take 3 steps to get there in the shortest possible way. What about this example? We start here and the food is here, but as we can see, there's a wall blocking us in basically all directions. So in this one, it's actually -1 because it's impossible for us to go through the obstacles and get to this piece of food. In the third example, we're here and there's 2 pieces of food here. So it doesn't matter which one we go to, we just want to go to the one that's actually closer. So I guess it does matter which one we choose as long as it's the shorter one. So it's going to take 1 tile to get here, 2, 3, 4, 5, 6. And if we wanted to go to the other one, it would take, 1, 2, 3, 4, 5, 6, 7, 8. And we can, go through the other paths, but this first path that we took is going to be the shortest one. So as you can see from our problem, we have a starting location and we want to get to an end location in the shortest amount of steps. So if you've seen this channel before, you know that we've done a ton of these problems, and anytime you hear shortest path, the first thing that you want to think of is going to be breadth first search. So what we want to do is just kick off a BFS from our current position and try to reach the food. The first piece of food that we encounter will be the shortest path to the piece of food, because remember that breadth first search will check all paths of length 3 before it does any path of length 4. So that way, if we reach the first piece of food we reach will always be the the global minimum path length. So all we need to do is we're going to need to first find our position, because we're not actually given our start position, we're just given the grid. So we need to perform, a traversal through our grid to first find our position. And then from the position, we just want to kick off our BFS, and we're going to need some sort of visited set to keep track of the tiles we've been to make sure that we don't get caught in an infinite cycle. And when we reach our piece of food, we can simply return how many steps we've taken so far on this path. And if our queue ever breaks because it's empty and we haven't found a piece of food, then we know that it's actually impossible to reach it, and therefore we can just return -1. So let's go to the code editor and type this up. It's going to be super simple, pretty standard binary search. Sorry, not binary search, breadth first search. So I'll see you in the editor. Let's code this up. We know that we're going to be working with a grid, so let's define some variables to help us with the size of the grid. So we're going to say rows is going to be the length of the grid, and the number of columns is going to be len grid 0. All right, we need a few data structures. Remember that we're going to be doing a breadth first search, and typically we use a queue. So let's define that. So we're going to say queue equals collections.deck, and for now it's going to be an empty deck. So we also need a visited set to keep track of where we've been. So let's define it, and again, it's going to be empty because we haven't actually done anything yet. The first thing that we need to do is realize, okay, we're given a grid, but we're not given the starting position, which is this star here. And we're told that there's exactly 1 star cell. So the first thing that we need to do is actually go row by row, column by column, and figure out what our starting position is. So let's do that. So we're going to say for row in range of, can't type today, range rows, and then for call in range calls. what we're going to do is we're going to say if grid of row call actually equals to our start position, which is this star here, we're going to say we want to add that to our queue. So we're going to add row call, and then we're also going to add the number of steps we have taken, because we need to track what the shortest path is. So obviously we've taken 0 steps at this point, and we want to say visited.add row and column, right? So we're going to break here to get out of our double for loop. And now what we need to do is we need to iterate through our queue, and remember that we're allowed to move up, down, left, and right. So let's define those directions. So we're going to say directions, so we can move up, we can move down, we can move to the left, and we can move to the right. Okay, cool. So now that we have that done, we need to process our queue, and as soon as we reach a a hash here, that's a food cell, and that's going to be our best answer. If the queue ever ends because it doesn't have any elements left, we'll know that it's actually impossible to get to the food, so we can simply return -1 if that's the case. So let's process this. So we're going to say while queue, we're going to say that the current row, the current column, and the number of steps we've taken is going to be whatever we pop from the top of the queue. And now let's double check that our current row and current column position is not actually a food cell. If it is, we can just return the number of steps. So we're going to say if grid of current row and current column actually equals to a hash here, then we can simply return the number of steps because we found a solution. Otherwise, what we need to do is we need to basically figure out all 4 directions we can go in and make sure it's a valid direction. So we're going to say for row increment, column increment in directions. What we're going to do is we're going to say that the new row is going to equal the old row, so current row, plus whatever the row increment value is. We're going to say that the new column is going to equal to the current column plus the column increment. And now what we're going to do is we need to check whether or not this new row column coordinate is actually valid. So it's actually within the bounds of the grid, and it's not an obstacle, right? Obstacles are marked with X, so there's no point of us going into it. So we're going to say if, so let's say if we're within the bounds of our rows, so if the new row is less than or equal to 0 and less than the number of rows, and we want to make the same check for the columns, so the new call is less than the calls, and we actually want to make sure that our new row and new column does not actually equal to an X, because if it's a obstacle, then we don't care about it, we can ignore it. So let me just move this over so it doesn't get indented weird. Now that we have that, okay, now what we need to do, now that we know that our new cell is actually valid, let's make sure that we haven't actually visited that cell before. So we're going to say if new row, new column, not in visited. So if this is the first time that we're going to be visiting this cell, then we can say visited.add, and we're going to add that new row and new column to indicate that we're visiting it, and we're going to add it to our queue for further processing. So we're going to say new row and new column, and then steps plus 1, because obviously we will have now made an extra step. So in this while loop, either we're going to return steps or the while loop will break because there's nothing left in our queue. If we get to the point where there's nothing left in our queue, that means that we were not able to find a path from our starting position to one of the pieces of food. Therefore, the problem tells us to return -1, right? If you cannot reach any food, return -1. So let me just run this, make sure I didn't make any syntax errors, and it looks fine. And let's submit this, and we are good. All right, so what is the time and space complexity of our algorithm here? Well, this is a pretty standard breadth first search. So if we just think about this, in the worst case, the starting position is actually going to be the very last element in our grid. So it's going to be like the bottom right corner. So to do that, it's going to take O of m times n, where this is the dimensions of the grid. So that's just to find our starting position. And then our queue here, in the worst case, we would have to traverse basically, all the way somehow, I don't know, just like up and down. We'd have to visit basically all the cells. So depending on how far we have to go between our start and our endpoint, they could be, at the maximum possible distance from each other. And this is also going to depend on the size of the grid. So it's just going to be big O of m times n. So ultimately it's going to be 2 times big O of m times n, but we know that constants don't matter asymptotically, so our runtime complexity is just big O of n times m. So basically how big the grid is going to determine what our time complexity here is. So for the space complexity, it's going to be the same thing. Our queue and our visited set could potentially end up storing every single cell in the grid, which means that our space complexity is also going to be big O of n times m. So pretty straightforward. This is another one of those problems that you solve using the pretty standard breadth first search template through a 2D grid. You set up your directions, you go in all 4 directions, make sure that your new column position is valid, and then do something and make sure that your BFS stops when you reach the target or some other condition. You see this so much. I have tons of problems on this channel where we use the exact same template. So this really should be nothing new for you. If you want to watch those other videos, there's a playlist for, I believe, 2D grids or BFS. So you can brush up on those if you're feeling confused. Anyway, that was the solution for this problem. If you enjoyed this video, please leave a like and a comment. It really helps with the YouTube algorithm. If you enjoyed this video and want to see more, please subscribe to the channel. I have a lot more content coming up, so you don't want to miss that. Otherwise, thank you so much for watching.